Rust.
No, okay.
Maybe I will just.
I guess I'm probably also.
Which one is for you?
Yeah.
This is me.
But when it says either have title has to or
Yes.
or has question mark.
It's on Saturday.
Back on?
Okay, welcome to the last session of the day, and we're very happy to have Larry Yaffe give us a talk towards a numerical solution of large N QCD. Yeah, when I was a graduate student here, Larry was a professor and was very helpful to me. I ran numerical calculations on his computer. Called the Ridge.
That's right, the Ridge. Thank you, Igor. It's a pleasure to be back here for the first time in quite a few years. So I recently completed a term as department chair, 5 years, including covering the pandemic. And since I've stepped down, I have rediscovered the possibility of actually thinking for more than 5 or 10 minutes at a time about a problem, which had not been true for years. So many of you know this, but there may come a time where you can't. So I had to decide, what am I going to think about? And, well, we've had talks here, which I think is fair to describe as very clever work. I think when I'm going to talk about, the relevant description is more like persistent, stubborn. Whether pig-headed applies, time will tell. Maybe it's Poincaré recurrent. But yes, I want to talk about the feasibility of solving numerically large N Yang-Mills, large N QCD. I want to make clear I'm not talking about 1 + 1 dimensions. There's interesting physics there, but not for me. So 2 + 1, 3 + 1, real world. And the basis for this has been known a good long while from not only my own work, but I happened to put that thing out a long time ago, that the large N limit is literally, in detail, specifically, a type of classical limit. So that's to say the large N quantum dynamics in sectors of gauge invariant states reduces to classical dynamics. There's a classical phase space, there's classical Hamiltonian, all the usual, symplectic structure that we teach about. And it's unremarkable in many regards. So the phase space is essentially just the same as the space of an overcomplete basis of coherent states that you can define. They're nicely generated by a Lie group. It's an infinite dimensional Lie group. It's a group whose Lie algebra is essentially a linear combination of Wilson loops, spatial Wilson loops, and their conjugate momenta, which are essentially their time derivatives, or in a Hamiltonian description, Wilson loops with one insertion of an electric field operator. What's to say? The classical Hamiltonian is nothing but the rescaled expectation value of the quantum Hamiltonian in this space of coherent states, which you interpret as now just a function on phase space. Expectation values just turn into functions on phase space. And importantly, large N factorization here is just, again, the statement that expectations of products of sensible operators turn into products of their corresponding expectation values. And dynamics comes in that commutators turn into Poisson brackets, which emerge from the Lie algebra structure of the phase space. What I just said is sort of clean and simple for pure Yang-Mills. So you're rescaling by a factor of n squared, but you're free to add fundamental representation fermions. It gives you a structure of a nested limit where basically you solve the pure gauge dynamics first, and then the fermions, this is with number of flavors, tiny compared to the number of colors, basically give you subleading order n classical dynamics. It works perfectly nice. So this has been known for longer than the lifetime of many people in this room. What's the problem? You got classical dynamics, you got a Hamiltonian on the phase space. If you're interested in vacuum or near vacuum properties, roll up your sleeves and find the minimum of the Hamiltonian. Get on with it. And just like one teaches in elementary classical dynamics, once you find the minimum of a Hamiltonian, assume it's an isolated minimum for simplicity, you expand around it. You get small oscillation frequencies. Those classical small oscillation frequencies directly tell you the large N limit of excitation energies in the quantum theory, or in the context of QCD, directly tell you things like the blue ball and the meson spectra. You expand further, you get cubic terms, you get quartic terms that directly tells you the large N limit of things like 1 to 2 particle decay widths. Even though those scale like 1 over n, it's information that's encoded in the leading classical dynamics, or 2 to particle scattering amplitudes. It's really just like calculating tree graphs in a weakly coupled theory, but you're expanding around the minimum of a large N dynamics. All the counting works the same. So, roll up your sleeves and do it. No stochastic sampling, no Monte Carlos, no DMRG, no sign problems, no quantum computing. This should be the warm-up problem. Now, of course, to really do this, you need the theory to be well-defined. So UV regulate it, put it on a lattice. I'm talking in Hamiltonian language, so think about the same Hamiltonian lattice gauge theories that multiple people have talked about already.
Have you tried this in 1 + 1 dimension?
Yes, when you were a student.
He didn't read your review.
So, I mean, of course, this is general structure. You can apply it, for example, in the one plaquette model, the simplest possible Hamiltonian lattice gauge theory. You can do everything by hand, analytically, it all works beautifully. But that's a case where the amount of gauge invariant information is less than the naive amount by a factor of n, and as soon as you have multiple plaquettes, that's no longer true. So anything beyond just one plaquette is more challenging. Okay. So more recently, in thinking about this, I had to think about, or anybody who wants to perhaps think about this has to answer a number of questions. The first of which I regard as a very serious question, is doing this worth the trouble? That's actually closely related to the next point. I just talked about this in a sort of a Hamiltonian framework. There's a very parallel Euclidean discussion where you think about it as statistical mechanics. You think about solving the Euclidean theory as that of minimizing the free energy over all possible statistical density matrices. In large N, there's a much smaller subset, again generated by some infinite dimensional Lie group, of density matrices that automatically solve large N factorization, so you can reduce the minimization of the free energy to this subset. So, is it worth investing the time and effort? I'm going to talk about that a little bit. If you're going to do it, well, I said there's the space of coherent states. You have to have some way of just labeling them. It's just like choosing coordinates on a classical phase space. There's no one way of doing it. You've got to choose something. You want to minimize the Hamiltonian. It's variational. You got to choose what your variational parameters are. It's infinite dimensional. And this is a key point. Vast numbers of infinite dimensional minimization problems are straightforward. I mean, every finite element method. I mean, gosh, you name it. I mean, string dynamics. I mean, any number of problems we're used to saying, yeah, it's infinite dimensional, but there's a very straightforward way of approximating the system with some sequence of finite dimensional truncated problems, and then you see how it converges, and hopefully life is good. So a huge issue is just the practical one of what's your truncation scheme, how well is it going to work, and what does it take to do it? Okay, well, is it worth the trouble? One can say things have changed a little bit in 40 plus years. More than a little bit. Of course, the state of lattice calculations is enormously advanced from what it once was. We have fully controlled calculations of a growing number of physically relevant observables, including parts of the spectrum, weak matrix elements, thermodynamics, and so on. We have everything we've learned from holography, which is a very specific realization of exactly what I started with, right? Holographic duals give us a classical dynamics which just kind of miraculously is local in this higher dimensional space, reflecting exactly the general structure I talked about. But, well, first of all, we don't have a holographic dual of real QCD. Lattice theory has made lots of progress, but extracting real-time information is still really tough. So in just my own judgment, if the only goal was to do a hard calculation to extract, say, the expectation value of a particular Wilson loop on a Euclidean lattice, I kind of have trouble justifying it. I mean, for that, you might as well go do a lattice simulation, and we know that there's very weak dependence on the number of colors. But the same argument that has been made for decades, I think, still holds. That's what's really interesting is the potential to do, in this Hamiltonian approach, to expand around the minimum and directly get real-time information that will let you get at not just the spectrum, but the k-widths and scattering amplitudes. And that's just as interesting today as it was years and years ago. So that still motivates me. So I want to talk a little bit about sort of different approaches. And I forgot to say something I was going to emphasize at the beginning, but you all know this. My title was Towards a Numerical Solution. you shall all understand what it means to put that in the beginning of a title. It means you don't have results. That's true. That's absolutely true. So my goal here is to talk about some of the choices, the issues in approaching this problem, the choices which I think are most promising, and to give you a, well, status report on what I've been able to do building a system which was hopefully going to do this just in the last 3 months of effort. But I'm not there yet. Okay, so you got some classical dynamics on some big phase space. You can't analytically write down a formula for the Hamiltonian. You can't analytically minimize it. You want to teach a computer to do it for you. The first thing you need is some way of labeling where you are in phase space. You need some coordinatization. There's no right answer. And I'll talk about several possibilities. But I want to emphasize one big positive here. I'm going to choose, well, this is a choice, it's not the positive. I'm going to choose to focus my attention on properties in states that are translation invariant. Right? I'm assuming translation invariance is not spontaneously broken. I'm assuming that things like the expectation value of a Wilson loop doesn't depend on where it is in space. So in contrast to some of the other approaches we've heard about, everything I say you can work directly in infinite volume. You know, I am assuming that relevant lattice symmetries are never spontaneously broken in the theories we're interested in studying. Okay, so what does it mean to, say, pick a particular coherent state? One way of saying what state are you in, pure gauge theory, Hamiltonian lattice, is to simply say, let me give you a list of Wilson loop expectation values. That is to say, for every possible closed loop, but identified according to lattice symmetries, say, here's its expectation value, 1 plaquette, 2 plaquette, figure eights, arbitrarily complicated. That infinite list amounts to one choice of coordinates on the classical phase space. So literally, you can say, and I'm going to use little w subscript gamma. Gamma is just a generic index labeling some closed loop. W gamma is that Wilson loop. So those loops plus their conjugate momenta is one choice of coordinates on phase space, and you can really try and work with it. Just challenges. Another idea that also goes way back is to say that for translationally invariant states, there should be an encoding of the information in the vacuum state or equivalently in one of these coherent states by just giving somebody a master field. And in this lattice context, that amounts to simply giving you some matrix for links pointing in the x direction, a different matrix for y, a different matrix for z, and so on.
But this master field, it's just, say, gluonic field, not Wilson loop, or what is master field?
So the way I just described it, I give you a master field for each direction of link, and then if you want to build a Wilson loop, you literally just multiply up this fixed master field around the loop, take the trace, that's your answer.
So it's like a master gluonic field, right, in a sense?
Exactly, exactly. I'm ignoring the fermions for the moment, there's a story for that. So I'll say a little bit more about this. It has an appealing simplicity to it, but there are issues. I'm also going to talk about something that seems a little more complicated, which is I just give you a list of Wilson loop expectation values, and I give you a list of expectation values of Wilson loops in which there is an insertion of an electric field operator on the loop, or there are two insertions of electric field operators. That is redundant information, but there's good reasons why that's interesting. All right, big issues, obviously. I mean, any of these schemes, you got to truncate. What is the truncation error? Is it consistent? So I'll come back to that quickly. Any variational scheme, you need to choose some basis for how you move in the phase space. In other words, what your variational parameters are. Again, you have choices. You can just view Wilson loop expectations as those parameters you're dialing. You can say, well, I've got this master field, and I'm just going to vary each one of its matrix elements. Or you can do something a little bit more formal, which is to say we have this phase space. It has some geometry. It has geodesics and can define Riemann normal coordinates. So about any point, you basically have a group structure that lets you define what it means to move in a straight line in different directions. Writing that out just slightly, a little more formally, any coherent state is an exponential of some unitary operator, which is an exponential of linear combinations of Wilson loops or Wilson loops with one electric field insertion. That's true, but that's a mess. But instead of varying the parameters here directly, a nicer way, which technically defines Riemann normal coordinates, is no matter where you start, you just hit it with some infinitesimal Lie algebra element, or equivalently, its variation is just the action of a Lie algebra element acting on your state. And those Lie algebra elements are precisely these linear combinations written here. Okay, what are you actually going to do? So I'm going to talk about 3 different strategies real quickly. One is just list Wilson loops as your information for some finite set. You've got finite resources, keep some finite set of loops, forget everybody else, and treat individual Wilson loop expectations as variational parameters. There's a variety of issues. Obviously, how big is that set? How big is the error? The underlying assumption is, I should emphasize exactly what Martin talked about earlier this morning, which is it's all tied to the correlation length of a theory. As in all lattice calculations, there's a bare coupling on the lattice. Things are easy in the strong coupling limit. We'd like to go to the continuum limit, which is weak coupling. The correlation length gets longer and longer. Any calculation is going to get harder and harder. The question is always, can you get to sufficiently large correlation lengths to be interesting, to be able to extrapolate? Okay, with this approach, there's other issues. Wilson loops obviously satisfy inequalities, like scaled appropriately, they have to be less than 1. That's the first of some infinite hierarchy. So if you use them as coordinates, there's boundaries on what's the physical domain. That's a big deal. That's related to the Gross-Witten phase transition in the one-plaquette model. Recently, there has been some nice work by some of these people that is really using, well, bootstrap is just the buzzword, but basically developing methods which really respect those consistency conditions from the outset. And that's clearly a nice idea. And there's been some nice work in matrix models.
Also in lattice gauge theory also, right? Yeah.
Mostly permission matrix models with some limited exceptions. All right, in this approach, I can't really get into it, but in the Hamiltonian language, the kinetic energy is the square of the electric field operator. You've got to be able to evaluate its expectation value. Given what I've said, you can say, well, you must be able to express that in terms of Wilson loop expectation values, and you can formally, but it's a bit of a mess. And the tricky thing I want to emphasize here is there's this loop joining matrix, which basically says take an arbitrary Wilson loop, take another arbitrary Wilson loop, differentiate, or in other words, commute with the electric field on some site, each one of those loops, and join them together. So it defines, it's like defining the inertia tensor in some multivariate classical dynamics problem. It plays the role of the inertia tensor, and you need to invert it to evaluate the kinetic energy. And a nasty feature is that inverting a truncated approximation to this matrix is not a terribly good approximation to a truncation of the properly inverted matrix. It's not sufficient. sufficiently diagonally dominant. So that, combined with these issues of boundaries, makes me less than thrilled about that approach. Then there's the master field approach, where I think for Hermitian matrix models, some of the recent work is really very, very interesting and promising. What I want to highlight is specific to unitary matrix models, or specifically to Yang-Mills theory. And it's this fact that you better be able to describe the infinite coupling limit well, or you'll never be able to describe weaker coupling well. And in the strong coupling limit, the expectation value of every Wilson loop vanishes, except the trivial loop that's just defined to be 1. Now, if you have finite dimensional, some m by m unitary matrix, you get to pick it. For every link in the same direction, you get to pick one such matrix. You can try and find matrices which will make the trace of a product around a plaquette vanish, and you can succeed. And then you need to make the trace of a product around 2 plaquettes vanish, and so on and so on. And it just doesn't work that well. Which is to say that no matter, so you always have loops whose expectation value is non-zero, and the way it scales, especially as you go up in dimension, gets worse and worse.
May I ask you at this point, my old recollection is that in some ways this kind of, when you calculate the amplitude of loops, it's like a high order in 1 over n. So then, say, vanishes would be kind of the effect of that you need to go further, or I'm wrong.
No, this is all leading order in n.
Yeah.
Now, it's true in the lattice strong coupling expansion, you know, the most important loops are the ones that are small. Bigger loops have expectations suppressed by more and more powers of 1 over the coupling. Okay, so, I mean, this is something that I actually looked at with some of my then students many decades ago, not just many years ago. And it just appeared to us to scale poorly. So it's like an approximation to a master field that's 30 by 30 or 100 by 100 or 1,000 by 1,000 is probably not even in the ballpark. That if you're trying to do 3 dimensions, you're looking at master fields that are probably millions or bigger. And then just the computational effort of multiplying them around big loops, it's nasty. Which leads me to my third approach, which you can probably tell is my preferred one, because you're getting my pitch on it, which is still to keep a finite set of Wilson loops, because I don't know any more efficient way of storing things in a computer. Plus loops with up to 2 electric field insertions to use Riemann normal coordinates as my variational parameter. What that means is you analytically derive geodesic equations that tell you how the expectation value of a given Wilson loop varies as you move in a direction that's determined by some choice of your Lie algebra generators. So that's analytic, you do that once. But you're still truncating the set of loops. Back in the 80s, the approach was, well, just throw everything away that wasn't in the set of loops you kept. And for 1 plaquette model worked great. For 2-dimensional Yang-Mills, without transforming to plaquette variables, it was not bad, but challenging. I mean, for 2 + 1 dimensions, it wasn't that great, but computers have gotten a whole lot better. But what I think is also a big deal, but this is now speculation, is that one should be able to do a lot better by saying, well, I know I'm going to make an error by not keeping all loops, but can I do a better job than just setting to 0 the expectation values of all the loops I'm throwing away? And so an obvious idea is to just say, well, can I find a better approximation which replaces some big loop I'm going to throw away with some function of smaller loops? And the obvious point here is when we talk about long loops, almost all loops self-intersect. Now, in an SUN gauge theory, the trace of a loop which is self-intersecting, or in other words, is the composition of two separate loops, does not factorize and equal the product of expectations exactly. But it's not that bad. It's approximately true. It's true to leading order and strong coupling. It's approximately true in weak coupling if Wilson loop expectation values are well approximated by a combination of area law and perimeter terms. So it should be better than at least just setting them to 0. Okay. I already said I like this. The reality is, actually putting this into practice is well defined. It's complicated. You've really got to roll up your sleeves. And something I should have emphasized earlier is this is, in a sense I will not make technical, it's an exponentially hard computational problem. But physically that's obvious. I mean, as the correlation length gets larger and larger, the number of loops as measured by any measure of their size grows exponentially. So as you push to weaker and weaker coupling, I just think it's obvious that the resources you're going to need, you're fighting exponential growth, which is always hard. So that means if you're going to try and do this, you better do a damn good job trying to make it as efficient as you can. Now, computers have gotten a lot faster, but you're fighting exponentials. So this is what I basically just said. This is what I basically said. And yeah, so you better work hard. So I'm 3 months into trying to do this for the first time in 4+ decades. This whole problem, I think, has been pretty dormant, except for some recent work in these matrix models. I think this is an interesting time to get back into it. This is the approach I'm using. As I've talked about, I'm writing code in C++, which I didn't know terribly well. But I mean, I've done a lot of stuff in higher level languages. I just think you pay such a price, both in memory and in time. This really requires working harder. So, status report. You've got to decide how to encode all these loops with their decorations. I've could spend lots more time telling people about how I'm coding it, but you know, the basics is simple, right? You're encoding a loop by just saying instructions. One step here, one step there, one step there, blah, blah, blah. That's obvious. You need to deal with lattice symmetries and symmetry projections. You have to be able to specify a particular irreducible representation when you do those small fluctuations. So you got to keep your program that. A huge issue is just redundancy. So in a 3-dimensional lattice, the number of rotations, reflections, and such, the number of elements in the cubic symmetry group times charge conjugation is 96. But if I'm talking about a Wilson loop, nobody tells you what point starts. So if a loop is L links long, there's L different ways of specifying exactly the same loop, just cyclically permuted. So there are, you know, for typical loops whose length might be, well, let's say 100 for simplicity, in 3 dimensions, that gives you 10,000 equivalent ways. I mean, you have to reduce it to just one. There are trivial ways of doing it. Form all 10,000, alphabetize it, take the first one. You don't want to do that. So how to do this really quickly and efficiently is a big deal. I can talk about it, but that's done. You've got to work out commutators. So this is where you teach it, you know, how to vary things. That's basically done, and that's what leads to generating these geodesic equations and analytic formulas for evaluating the gradient and curvature of the classical Hamiltonian, which is what you need to do a Newton minimization to find a minimum. And then there's the whole, well, then there's implementing my new loop approximation scheme, not yet done. All the numerics, this is relatively straightforward, but it's just you gotta get it done. And then there's lots of testing on soluble models, and then application to not so soluble models. Whether or not this is a crazy thing to spend time on or not is not yet clear. It will be clear soon, but that's what I have to say. Thank you.
Thanks for a very interesting program you're sharing with us. Questions?
Thanks for this. I just didn't get what's the reason for choosing Hamiltonian? Just to go to have one dimension lower, the choice between Euclidean and Hamiltonian.
That's part of it. So dealing with spatial loops instead of space-time loops. But equally important is this fact that in the Hamiltonian formulation, you can directly get at the small oscillation frequencies just from expanding around the minimum, whereas in a Euclidean calculation, you'd simply be reproducing what everybody doing lattice simulations does, which is really looking at long distance fall-offs of propagators, which requires you have long separations. That's not what you want to do with this approach. You could do in the Euclidean thing like thermodynamic curvatures. That's much more accessible. So there's still interesting things one can do with the Euclidean formulation.
Thanks.
Roger.
Yes, this sounds very much like the problem that one would formulate also in quantum computing, right? So you're trying to find some path, geodesic path on some U to a manifold, and so that's to find sort of the variation of ground state.
I'm not trying to find a path. I'm trying to give you the answers for some property on all possible closed paths. It's sort of a different, yeah, it's not what the mapping app in your phone does.
Yeah, so you said the various different representations of the, of the Hilbert space, or not Hilbert space, the phase space. And then you chose in the end one. Did you have any? Is this based on sort of how much of that is intuition? How much did you actually try numerically to see which one works better? And
So I didn't really stop and say this. Oops. Here we go. I invite you to look at especially this paper here from quite a few years ago. Well, the first one, this one explicitly did the version of the master field. If you look at the page numbers, you can see I was a very, very slow learner about the importance of writing short papers. So from old work, looking at essentially all of these methods applied to a variety of testable theories, I'm giving you sort of the lessons that I take away from it. But it's an open question, whether that perspective is correct.
I think Henry Lynn.
Yeah, maybe one question is whether you tried, even 0 plus 1 dimensional, but just matrix mechanics, for example.
I mean, if it's one matrix, any of these things work great, but that doesn't count.
But there, I think Antal's collective field approach, right?
If it's two matrices and they're Hermitian, I think Antal's work is really quite interesting.
I meant 0 plus 1 dimensions, not just 0 plus 0, maybe.
Well, the collective field approach was 0 plus 1.
Yeah, I mean, so 0 plus 1 would include just like two Hermitian matrices quantum mechanically.
Right. But
So that already, illustrates all this stuff. There's some interesting recent work. But as soon as you make them unitary, you face exactly the same issue. That you have you know,
I don't really
products,
understand.
single trace products whose expectation should, an infinite set of them whose expectation should vanish identically, but you can't encode that with finite dimensional master field approximations.
Isn't there the same issue even in two matrix quantum mechanics, just because you could have x's and y's in various
Yeah.
orders?
Absolutely, absolutely.
So does this method like work in that case, I guess is my question.
I believe so. So, but just to be clear, I mean, I use the language of saying I'm looking at an infinite Hamiltonian lattice gauge theory. When I say I'm focusing on translationally invariant states and the observables are simply Wilson loops where I just give you a sequence of walking directions, that then looks exactly the same as Hamiltonian quantum mechanics of 2 or 3 matrices. I mean, it's the same set of observables, it's the same complexity, but the issue is, are they Hermitian, are they unitary, what are the couplings?
Maybe one could compare it with, like, for example, the results that Josh will present. I think, roughly speaking, it sounds to me like the difference is here you make some ansatz whenever you, so you impose some equations of motion, and whenever you involve a correlator that you don't have in your set, you impose some ansatz to relate it to something that you already know, right? Whereas in the other approach, in the bootstrap approach, you just derive some bounds, so you don't have to make any ansatz. But you could compare it in the situations where there really are these nice convergent results and see whether the ansatz is correct.
Oh, absolutely. But this is just sort of a question of perspective. I mean, finding bounds, that's great, it's lovely work. I approach this more like, I just want an answer. I want the best answer I can generate. So, you know, if I can do a calculation that retains correctly, exactly all the dynamics of 100,000, a million loops up to, you know, this size, I think that's well beyond what the exact bounds are ready to get to in the near future. But we'll see.
All right, well, let's thank Larry again.